And this was a successful program, as you will see, with demonstrators built and tested. And if we go to the next slide, this is a brief introduction to iNEMI by Grace.
Yeah, sure. Thanks, Terry. And this is just for people who aren't familiar with our consortium. And what we're about really is enabling everyone to move faster in terms of deployment of their new technologies and innovation. So we work on forecasting what's going on in the industry through developing industry roadmaps, everything related to electronics manufacturing. And then out of that, we work together on key challenges that say this supply chain or value chain for electronics manufacturing has. So, and this is one of, I think this project addresses some of the, exactly that in terms of some of the key challenges that we have in enabling photonics packaging and co-packaging to move further. So if you need further information on iNEMI, you can find it on our website. But I think today we'll concentrate on the results of the project.
Okay, thanks, Grace. So this is the agenda. The bulk of it will be Camille Grakowski presenting the technical results from the program. I will give you a quick overview of the program motivation and objectives, as well as some past projects that led up to this, how we came up with the target design specifications, who was involved, and why we chose the expanded beam interface design. And then quick overview of some of the publications, presentations that have come out of this, as well as some of the special challenges that we faced due to supply chain issues, et cetera, and who the key technical contributors were on the team. And I'll show you where we want to go next with phase 2 of this program. Okay, so the motivation for this is that the industry roadmaps predict that silicon photonics is going to be the most cost-effective and energy-efficient solution for onboard interconnect in the future. And a key component or feature of silicon photonics is that these are single-mode devices. So they need single-mode interconnect media. The connection of single-mode waveguides to single-mode fibers is something that is very tight tolerance in terms of alignment. So that is one of the reasons that packaging of photonic integrated circuits, or PICs, is difficult and expensive, because you have to achieve and maintain that submicron alignment. Right now, coupling the PICs is typically achieved by direct bonding of the fiber to the PIC, resulting in a pigtail package. Pigtails are not ideal because they're not compatible with going through reflow on a printed circuit board, and they complicate the handling and placement of the modules that have the pigtails. So another issue is that for very high port count interfaces, the current single mode connectors that rely on physical contact between single mode cores require a very high mating force. And so we'd like to go to expanded beam non-contact connectors to relax alignment tolerances and reduce mating force. Next slide, please. Okay, so the main objectives of this project, as proposed, are to demonstrate the principles of a separable, meaning connector-based, single-mode expanded beam connector to the chip interface by building the modules and testing them and verifying the optical performance, and to assess manufacturability and assembly issues for such systems. Next slide. Okay, this did not occur in a vacuum. iNEMI has been involved in expanded beam connector activity since about 2014. Tatiana Berdinsky, then at Celestica, led a program looking at the impact of contamination on multi-mode expanded beam connectors. Tom Maripode from Molex led a program on development of connectors for mid-span cable-to-cable connections with single-mode fiber. And then I led an effort to survey users of technology and figure out what would need to be used according to the customers for connections to photonic integrated circuits, whether people thought that edge coupling or vertical coupling would be the dominant approach. And this involved a survey of 99 stakeholders across a wide range of industry sectors and participants. And I'll show you what some of those specifications were in a minute that came out of this. Next slide. Okay, so what came out of this survey was that people wanted a pluggable single mode expanded beam interface. They wanted optical coupling at the edge of the PIC instead of vertical coupling. They wanted less than 2 dB waveguide to fiber coupling loss, horizontal mating of the connector to the PIC module rather than vertical coupling, fiber exit parallel to the board so that you can keep a low profile board, non-hermetic package, and PIC design that's compatible with testing at the wafer level. And then a stretch goal was reflow compatible package. And that actually has been demonstrated that you'll hear from Camille. So the targets that were driven by the availability of parts, 8 channels of optical signal at a 250 micron pitch, 12 fiber ribbon cable. Okay, next slide. The participants in this program, you see here, mainly led by Tyndall, with participants across the spectrum of industry leaders, suppliers of various different kinds of components and design expertise. Next slide, please. Okay, so what do we expect to get from this design? The expanded beam connector relaxes the lateral alignment tolerances required between the cable connector and the modular receptacle, minimizes the impact of dust on the optical performance. That can be especially important in a backplane type connector, and it allows low insertion force connections. The separable module interface, as I mentioned earlier, simplifies the mounting of the modules on the PCB. It's required for reflow because you don't want the cables to go through reflow. Facilitates rerouting of cables, facilitates changing out transceiver modules for upgrades or repairs, and eliminates the need for inventory of a range of pigtail lengths. Next slide, please. So this part of the presentation is Camille's description of the technical work. Camille.
Thank you, Terry. So my name is Kamil Gratkowski, and as Terry mentioned, I work at Tyndall Institute under Peter O'Brien, and I led the majority of the groundwork on this project, so I'll be presenting the technical results. And I'll start by mostly restating what Terry mentioned as the objectives in the more graphical form, so that you can appreciate the objectives and the difficulties that we're trying to, and the problems we're trying to solve here. So the typical state of the art is that we permanently bond. As you can see, there's a thin layer of epoxy between a photonic integrated chip and the fiber array. And this occurs for both the grating and in edge coupling paradigm. So this is you can see here the bonding process being done in one of our machines. However, this is a package level process. So as the package has to be 99% complete, and in majority of the cases, the attachment of the fiber pigtail is the last thing to be done. So this is a highly serial process that is difficult to scale up. Additionally, as Terry mentioned, we're dealing with very high, very tight tolerances. So depending on the mold field diameter that you might have on the edge of your chip, you might be dealing with sub-micron tolerances up until, let's say, several 2.5 to 3 micron tolerances if your mold field, if your spot size converter goes up to 10 microns. And just for the purpose of definitions, I'll be defining the element tolerance as displacement or angle at which the optical signal decreases by 1 dB, or about 80%. And coming back to the tolerances and the issue of attachment and serial process, these both factors lead to the cost of packaging, assembly and packaging being a significant portion of the total cost of the package, as you can see by the breakdown on the right. So as Terry mentioned, our idea is to expand the beam between the photonic chip and the fiber. And this can be done by deployment of microlenses, so very small pieces of either fused silica or silicon that can be placed at both of the interfaces. And in between, the beam can be expanded. This is essentially following on the idea that, as you saw from the previous slide, as the mold size gets larger, then our tolerances get relaxed. So this is, let's say, the expansion of that idea, but we additionally want to not only expand, but also collimate the beam in between. So on the right-hand side, the fiber and the fiber lens will form something that we call connector coupler, and this can be an element that's completely independent. And on the left side, there's a separate micro lens that's placed on the photonic chip. And as I mentioned, between the beam is expanded and collimated, and there can be a significant air gap in between. Looking at the tolerance analysis from the Zemax simulation, we can see that primary result is that as we expand this beam in size to let's say between 50 and 130 microns, you can see that the element tolerances are increasing from around 12 to more than 30 microns. While previously we were dealing with single micron to 3 micron tolerances, in here we are already expanding those tolerances to several tens of microns. This, however, comes at the cost of the angular tolerance. The more we expand the beam, the more tighter the more susceptible we are to the deflections in the angle. So there is a trade-off that has to be considered for each package type. Additionally, which is also important for a contactless link, the components can be placed apart lens to lens quite at significant distance, and that also depends on the mold field diameter of the expanded beam. For the largest beams, this can be even significant fractions of a centimeter, while for the narrower beams, we are limited to, let's say, first 2 or 2.5 millimeters. However, this distance can be tuned by adjusting the conic parameter of the microlens. However, what is critical, and Terry has also mentioned, is that the connector coupler, so the fiber side of the connection, can be made completely agnostic to the photonic chip that is being used. That's because we can engineer this lens in order to couple to exactly or nearly exactly the same mode, and as long as that is satisfied, then regardless of the mold field diameter that we have, regardless of the mold field diameter, the element tolerances and also the coupling efficiencies can be made the same. So this simplifies the logistical aspects of packaging. And designing those the micro lenses is quite a simple affair because we have only a few parameters that we deal with. The only really big parameters that we have to consider is the mold field diameter of the source, as well as the target mold field diameter. So for this project, we didn't go with a complete redesign from the scratch. We wanted to use something that's easily that we can get easily off the shelf. So Molex kindly supplied their MT expanded beam ferrule. So that is our connector coupler that we have used. This was from this fiber to fiber expanded beam connectors. And David Stegall from 3M has made a simulation where he took some off-the-shelf lenses and he chose the best one, the best performing one over the air gap that we have designed. So the air gap design is the distance between the lenses was actually targeted so that there is a spacing between the chip and the beam ferrule, because there are some alignment features that have to be mechanical clearance. So that was the reason for this air gap. So the lens that best performed for the expanded beam ferrule, if by assuming that the mode field diameter at our PIC side was around 10 microns, was this lens from SUS Micro Optics from Switzerland. And David went on and has also done some sensitivity or alignment tolerance analysis for this. So the critical two things regarding sensitivity is that while the alignment of the micro lens to the chip is still a single micron micron issue, we can actually, by using micro lenses in between and expanding colorimetric beam, we can relax the alignment tolerances. So the number that the simulations tell us is about 22 microns for 1 dB additional loss due to misalignment. One more thing that's important to say is that at our designed distance of 2.1 millimeters, we didn't have the best insertion losses. However, that was the evil that we had to live with for this specific combination of micro optics. For the chip, we have within the Tyndall, within the packaging group and specifically PICSA pilot line, we have manufactured through the Lyonix foundry several of reference chips. So reference chips are small pieces, in this case of silicon nitride based photonic chips that are just there to facilitate what's the word? Development of photonic packaging. So they're just simple as possible. In this case, they contain just simple loopbacks or through waveguides at various pitches, and we can use those and we can get them en masse. So per wafer, there's we can get several hundred of those, up to several thousand, and we can use those to develop packaging technologies. So as the technology we used was silicon nitride, this had additional benefit in comparison to standard silicon technology, is that there was no special need to do any processing of the facet. Typically, when you're dealing with silicon chips, you have to either dice, and not dice, you have to either polish, etch, or cleave the facet to get a optically flat facet for efficient optical coupling. In this case, as the effective refractive index is close to 2, this facet can be effectively diced, and while in air, at the air interface, we get about 3.5 to 4.5 dB loss. Once you fill the gap between the facet and the fiber array, and the fiber with an index match liquid, in this case it was 1.55, the losses dropped to below 1.5 dB per coupler. So we took that chip, and in the demonstrator, we have first placed it on a ceramic submount, and then we have designed a mechanical mount around it. So this mount has several features which are important, and the interface here is the alignment sleeve that houses the MTP expanded beam ferrule, and we also have a top lid to cover it off, to protect it from dust. What's critical is the alignment of the MT expanded beam ferrule onto the chip, and this is facilitated by the alignment sleeve, which allows for coarse alignment. However, the fine alignment that really gives that single micron precision is the set of alignment pins that are part of the MT expanded beam ferrule. You can see And in this picture, you can see the holes on the side of the array, but what we had was the male connector. So this is the female connector, but over here we had the male connector, and they were interfacing with alignment slots that were built into the package. So these holes, of course, had to be manufactured with high precision, and another precision that was necessary was in designing of the stack. So we have a photonic chip, we have the sub-mount, and these two form the PIC assembly. And there also, we designed a gap to be between the sub-mount base and the PIC assembly. We designed to be around 100 microns. In the end, it turned out it's closer to around 70 microns. So we're still, the tolerances are tight, but they're acceptable. The packaging procedure is deceptively simple. The PIC is it only diced. It requires first cleaning, which is simple process enough. Then we place it on a ceramic substrate. The two active steps are attaching the microlens to the PIC, as you can see here, using the empty expanded beam ferrule and the shunts that are on the chip as a guide to the proper alignment of the microlens. And finally, we take this PIC assembly, which is containing the sub-mount, the chip itself, and the microlens, and put it onto the package. So in the first step, here what I want to show and appreciate is the tooling that has to be used for such precision alignment. Not only the stages have to have a single micron precision, but also the tools we use to pick up the lenses have to be quite precise. So the lens is just 600 microns in thickness. And in the packaging group, we have dealt with even thinner lenses. And you can see the tool that we used is a very fine set of grippers. And of course, if the grippers are too thick, then we are risking actually attaching the grippers along with the microlens when we apply the epoxy. So handling is critical. However, what's useful from using silicon nitride technology is that it's transparent to visible light. So it's a bit difficult to see on this picture, but this arrow shows the thickness of the lens. And if we shine red light through one of the channels at the shunt on the opposite side, we can actually see highlighted the output. So this is a nice packaging assistance method. The microlens attachment and application of epoxy was done in 3 steps. First, we applied the epoxy at the back and allowed it to seep into the gap between the chip and the microlens. This was done because the tooling is so fine that if we withdrew the lens and brought it back, there was a chance, however small, that the microlens could be deflected. Then we cured the epoxy using a mercury lamp, and finally we have released the microlens. So here you can see from this picture, there's actually first picture you can see that clearly shows the position of the alignment pins from the empty ferrule. So the distance is quite close. That's why this gap was around 2.1 millimeters in order to give us this clearance, as we were really close. The distance between the lens and the alignment pins was really close, so we had to have a bit larger of a gap. That's why in the simulation we were not at the optimum distance. This can be, however, engineered. The alignment tolerances that were measured all show what we expect. The most important graph is this one, where here you can show just the alignment tolerance of the micro lens. So this is still in single microns. I think this was 2.5 micron alignment tolerance. However, the tolerance of one of displacement of connector coupler is now around 15 microns. Now, previously I mentioned that the simulations showed around 20-22 microns alignment tolerance, and this is one of the issues that we have faced, and we're still working on it along with David Stegall. However, what we also see from this graph is that we don't have a nice circular mode coming from our chip, so it's slightly squashed in the X direction and it's expanded in the Y direction. David actually measured the mode size at 3M, and it comes out 6.5 microns in the X direction and 7.3 in the Y direction. So it's just below what we set out in the simulation. So this could be one of the reasons why the simulations and the experiment don't agree. Then we have the next step in the assembly was taking that microlens and chip subunit and putting it into the package. So first it was aligned against, again, the expanded beam ferrule. So, epoxy was first applied at the front in order to secure it, and then applied at the back. 2 prototypes were made. In the first instance, only epoxy was applied all around the chip. And in the second instance, the primary attachment point was at the front, so that the shrinkage of the epoxy that is inevitable part of curing didn't bring the assembly out of alignment. It actually brought them together closer without displacing them vertically from one another. So that was an improvement. So what we see in terms of coupling efficiency when we go through the process, all of these curves are taken with the microlens at the interface. So when there is an air interface, similar to what we saw before, we have about 2.5, 3 dB losses. Once we fill the gap with epoxy, this drops to around 1.3, and the curing adds additional 0.1, 0.2 dB losses. This is expected due to shrinkage. However, this can be, of course, controlled in a more automated environment. Then when we take this assembly and put it in a package, we start at 1.3 range, and due to shrinkage of the epoxy, we typically see some displacement or tilting, which decreases the coupling efficiency by 1.5 dB. So this is the one of the final demonstrators, one of the cover off and with cover placed. You can see here the epoxy is put all around quite generously. And for the plug operation, you can see here the video of me plugging the pigtail in and out. I'm going to run it again. Right, so here you can see the alignment pins, and this is the facet of the microlens array that interfaces with the microlenses on the chip. So as I mentioned, 2 prototypes were manufactured, and they both have similar performance in terms of pluggable operation. So first prototype was measured across 30 make and break cycles, and you can see that it clusters around 3 dB. However, the second prototype performed much better because we don't have this high loss tail. All we have against coupling losses centered around 3 dB. However, we have it's more towards the low end tail, and this was actually in total across 80 make and break connections, 50 of which were done immediately after packaging, and then 30 more on the following day. So this shows that there was no additional epoxy-based shrinkage losses that occurred.
Thanks, Camille. So I wanted to quickly summarize what has come out of this project in the way of publicity. One of the things that we wanted to do was keep the standards bodies aware of what was developing, so they could potentially be thinking about where they would go with expanded beam connectors in the future. So there have been 3 presentations for IEC standards committees that have been done this year, actually. We've also submitted a paper to the ECOC conference coming up in September. That's been accepted and will be presented. Camille is working on a more comprehensive journal paper, as the idea is to really describe everything in detail. We have not finished that yet, but that's in process. And then again, back to the standards committees, there's a meeting in October that where we will give them an update on the status of this program. Next slide, please. Okay, we encountered a couple of problems in the process of doing this. One started right at the beginning when we had problem with the foundry and their deliverables. And this is all back to the supply chain kind of problems that have been plaguing technology for over a year now. So we got our PIC samples a few months late. That kind of pushed the schedule a little bit. But by April, we had the technology goals largely met. There is a little bit of disagreement between the simulated and experimentally measured coupling efficiency. Camille and Dave Stiegel at 3M are continuing to work on understanding this. It may be that some of the values that were put into the model don't actually correspond to experimental reality, and so they're trying to figure that out. The team is going to continue to investigate this issue in phase 2 of this program. Next slide. So some of the key technical contributions that made this program possible. Camille kind of did a lot of the heavy lifting. He was involved in the package design, optical measurements, process development, and packaging. Dave Stiegel did a lot of the simulations and some of the optical measurements. Dave Mackey and Alan Naughton at Embryonics did the package design, mechanical modeling, and thermal simulations. Tom Maripode from Molex arranged for us to have the connectors and cable assemblies, and Taylor Foy and Alexander Hartwig from Dalo provided us with adhesives for the project. So I'm going to give you a real quick introduction to the next phase of this project, which the proposal for which is being developed right now. The font or the text in red is really the bottom line here. The idea is to take the assembly process that was used in phase 1 and demonstrate how that can be modified to allow automation so that this can be done at a manufacturing scale rather than by a highly skilled person like Camille in the laboratory. So we're in the process now of developing the proposal for this phase 2. And if any of you would like to join the team for that, I recommend that you contact Grace O'Malley and let her know that that you're interested. Okay, next slide, please. And again, this is just part of the standard documentation that we do for projects. And again, it's all about improving that alignment process. Next slide, please. Okay, Grace, you want to talk about the logistics of forming the next project?
Yeah, sure, because I know there are a number of people who are not familiar with iNEMI. So we use, a project development process with a couple of staged reviews as we go through it. And so we're now in the early phase here. Step 1, looking at the concept, and we'll be moving into defining and planning the project. That phase, the initiative phase, as we call it, is open to anyone in the industry to participate in. We welcome your insight and perspective as a user or someone along the manufacturing value chain for photonics packaging to be involved. Once the project then is finalized and moves into execution, only iNEMI members can participate in the project. But at least you get an opportunity in the early phase to get a very good understanding of what the scope and the commitment of being in the project would be. So I will be taking on that role or facilitating this initiative project, because Terry, who's been shepherding this work for the last number of years, both previously at 3M, where he worked for many years, and when he came to us at iNEMI, is going to go off and enjoy a very active retirement. And I thank him for all the work he's done so far in this area, and hopefully we as the team will be able to continue it now as we move into phase 2. So you have my contact details there. Please feel free to reach out to myself or Camille and Peter, who are also who chaired this particular phase of the project. We have a couple of questions. I'll look through those, but I'd like to Peter, you're also online. Did you have any comments you wanted to add to the presentation today, Peter O'Brien?
Yeah, hi Grace, hi everybody. No, just thanks to Terry and Camille for a very clear presentation. I definitely think there's real benefits. We're not trying to obviously say there's no need for fiber attachment. Of course there is, but there is a growing demand for looking at alternatives to bonding the fibers direct to the PICs, especially around things like being compact and being more, being able to fit into different types of very small form factor systems. So really, this project covers many aspects. It's not just the PICs, it's, as you say, the micro-optics, the epoxies, the mechanical design, and a lot of optical design and some process development. And there's no doubt about it, automation is the follow-on aspect of this, because we want to kind of take this to the next level. And we, in Tyndall, we're very much focused now, working with some partners around machine automation. So I think there's a good next step on that. So again, thanks to Terry very much, and Camille. We did have some delays. I think in general what we're seeing now is the supply chain is starting to pick up speed again. So I expect that we won't see those delays again. Hopefully not anyway.
Great. Thanks, Peter. Terry, did you want to introduce the questions?
Sure. Okay, so first question here is, when do you plan to evaluate environmental stability?
Maybe I can take that question, Terry, if that's okay.
Yes.
Yeah, so obviously one of the nice things about the iNEMI project kind of structure is it is and it's not. So of course we need to consider environmental factors, but it was decided within the scope of this project that we would not do it here. But that said, we are already looking at the epoxy materials, looking at things like, and it kind of relates to the next question as well, but around things like high temperature, solvent reflow, humidity, and so forth. Of course, that has to be considered. At Tyndall, we have a whole range of reliability test systems, humidity, thermal shock chambers, all of those kind of things. So absolutely. I expect with people interested in this technology, that's the next question. So, of course, we will be looking at all the factors that affect that.
Okay, thanks, Peter. The next question we have here is, in phase 2, is there an option to test other lens materials next to the epoxy? For instance, reflow capable thermoplastics that are IR transparent.
Maybe I'll just jump in and add my 2 cents, and then Terry, somebody else. But absolutely, I really do think there's an opportunity here for high temperature stable plastics, because what we're beginning to see is there's opportunities to bring more to the micro lens than just the lensing component itself. So other features, which are difficult to do at wafer level. So having an ability to shape the micro lens in a particular way, molded in a particular way is very, very attractive. And I think thermoplastics, especially ones that are stable and transparent in infrared, are very, very interesting. So of course, that would be of great interest.
Okay, thank you, Peter. I see Grace is asking for anyone who wishes to comment. She can unmute them. Any comments, anyone? Raise your hand if you want to comment.
If I can make one final comment here on the application. So we're looking at fiber connectivity, pluggability, but one of the nice kind of features of this approach is you have a collimated output beam, and that enables other applications that are not necessarily fiber-based. Free space, sensing, diagnostics, LiDAR, putting a micro lens on the photonic chip. You know, there's other areas that where there's, you know, not, as I say, not for fiber-based applications, but free space. So it kind of addresses those. It's a side benefit of this project.
Thanks, Peter. I will just add a comment here. We recorded the talk today, and that will be made available to you. We actually have scheduled a second live webinar session at the end of September, and Camille and Peter will be involved in that again, and that's to support I think the interest in other time zone areas. So it will be on the 29th of September at 9 a.m. London time, 5 p.m. Japan time, and you'll get information on that if there are others in your organization in different time zones or other organizations you want to be involved, or indeed if you'd like to come back and hear it all again and add some comments or questions at that point.